Now I will introduce you to a special type of series called geometric series. Okay, right. So to define a geometric series, we have a starting term, and then there is a thing called common ratio. Okay, common ratio, and I will represent it by R. So the way we construct the geometric series is we start with this, the starting term, and then we multiply this one with the given common ratio and write the next term, right? And then we multiply the second term with the common ratio and write the third term. And likewise we keep on multiplying the common like in order to obtain the nth term, we multiply the n minus 1th term with the common ratio, right? So this type of a series is called a geometric series. The special property of a geometric series is you just have a common ratio, that's all. Okay, so we can represent the common ratio in a sigma notation like this. Now before going into this series notation, now here you can see that this is the first term and this is the second term. Okay, this is the third term, right? This is the fourth term, and here it should be 3. Okay, because this one times r will be r to the power 3. Now see here, 1 means r to the power 0. See here, this you have 1, here you have 0, here you have 2, here you have 1, here you have 3, here you have 2, right? So whatever the number you have here, you have r to the power n minus 1. Okay, so that's a special thing that you should notice. So by considering all these properties, we can simply write down the sigma notation of a given geometric series. Like you can represent it like this, right? So you can see when you expand this given series notation, you will obtain the result before this one. Okay, so see here, if we substitute n equals 1, then the first term will be r to the power 0, and n equals 2, the next term will be a to the power r, a times r to the power 1, right? And for n equals 3, you will have r to the power 2. Okay, likewise you can represent the geometric series like this. Okay, and how did we define the sum or the convergence of a series? That is through through the sequence of partial sums, right? If the sequence of partial sums converge, we say that the series also converge and the values are equal. The limit of the sequence and this series value is equal, right? If it converge. And we can prove, now I am not going to do the proof here, and probably I will give it as a homework. So we can prove that if r is, the modulus of r is less than 1, that means if r is in between negative 1 and 1, excluding the boundaries, okay, excluding the boundaries, if it is in between negative 1 and 1, right? Here we have open brackets. Okay, if r is in this range, we can prove that the limit of the partial sum is equal to, the limit of the partial sum is equal to a over 1 minus r. We can prove this result. It is not obvious. Okay, you have to do some calculation. then we can prove that the limit of this one is equal to a divided by 1 minus r. Okay, so that means in other words, it says the series converges. Okay, that means if the r is less than, like if the modulus of the r is less than 1, the geometric series will converge. And we can also say that the sum is equal to a divided by 1 over r. Okay, we'll do some examples. And also there's one more thing. If r is greater than or equal to 1, if the modulus of the r is greater than or equal to 1, then the partial sum sequence will diverge. That means, this is the symbol for that is, the series, the geometric series will also diverge. Now this is a very important result that you have to remember. Okay, for a given geometric series, it can be represented like this, where this is the common ratio and this is the starting point. And if the common ratio, the modulus of the common ratio is less than 1, then the limit, we can prove that the limit of the partial sum is this one. That means the series converges and the series is equal to this. And if the modulus is greater than 1, the series diverges. Okay, we'll do some examples related to this one. Let's take the series, this one. Okay, so you can see the sigma notation. If we write the series in the sigma notation, it can be represented like this. So you can see a is equal to 5 and r is equal to negative 2 over 3. R can be a negative value, but then the modulus of r is 2 over 3, which is less than 1. So according to the thing that we said before, since the modulus is less than 1, the series converges. So that means you have a finite value for this series, and that value is equal to a divided by 1 over r. See, a divided by 1 over r. And here you are not taking the modulus. Okay, it is just the correct common ratio, so you have to include the negative sign as well. So everything will be like, if you simplify it correctly, you can see that the answer is equal to 3. So what we can say is, if you add all these terms, I mean all these infinite terms, you will end up with positive 3, right? And we'll do another example. If we consider this series, see, at once it is not of the form a to the power rn minus 1. Okay, but you can do some rearrangements like this. Here 2 to the power 2n can be written as 2 to the power 2 times n, because a to the power bc is the same as a to the power b to the power c. Okay, so you can write it like this. And then when you do the simplification, now this 2 to the power 2 is equal to 4, and that to the power n, and then this 4 to the power n can be written as 4 times 4 to the power n minus 1. So these two terms together, you can write it like this. Now see, we have rearranged the terms in the original series in this format, and by looking at this final format, you can see that it is nicely represented as our usual geometric series notation, right? So here a is equal to 4, r is equal to 4 over 3. But see, here the modulus of r, which is equal to 4 over 3, is greater than 1. So we can say that the series diverges. right? Now all these things can be done only for geometric series, okay? But remember, in the previous video we did an example, something like the sigma notation, sigma 1 divided by n plus 1, and this is not at all a geometric series. You won't be able to even convert this to a geometric series notation, right? So when it is not a geometric series, you cannot use these facts, right? So all these things are valid only for geometric series, right? And as the final part of the geometric series, let's have a look at this one once again. Now here, see, like here in the first term you have r to the power 0, right? So always the term number and the power of r has a difference of 1 unit, right? Here the term number is 2, here the power is 1, 3, 2, 4, 3, 5, 4. Likewise, there is a certain difference between the term number and r. So we can even get the same result by doing a slight change, and then both the term number and the power of r will be the same, right? So instead of writing the geometric series like this, we can even rewrite the same thing like this. Here the difference is you are starting the series at n equals 0, and here you have r to the power n. See, now if you expand it, now you have to start at n equals 0, right? So you have r to the power 0, and then n equals 1 will give you a to the power r, and n equals 2 give a to the power r2. See, you will still obtain the same expression, but now this term number and the power of r will be the same. So that is more convenient than it was before. Sometimes you might feel this as a convenient option, but you should keep in mind that we also use this representation for the geometric series. And the reason for telling this one is now we are considering a very special situation where a is equal to 1 and we represent r as x, right? So let's consider this case, right? So here a is equal to 1, so the first term is equal to 1 and I represent r as x, right? So then we have the series like this. Okay, so now we saw that now this is xn, likewise the series goes on, right? Now here we have, now our a is equal to 1, okay, a is equal to 1, so we don't have to write that down, and x is like the r is equal to x, okay, so here we can write it as x to the power n, n is equal to 0 and goes up to infinity, okay. It's just a change of variable names, that's all, right? And now the important thing here is, now we know that if the common ratio is less than or equal to 1, then we can rewrite the summation as, now we know that the summation converges, and also we can rewrite it as 1 minus x, right? This is actually a divided by 1 minus r, but here a was equal to 1 and r was written as x, right? So now this is kind of a standard formula that we should keep in mind, okay. Now if you know the equation of this geometric series, you can of course obtain this result, but sometimes without any mentioning about geometric series, we directly use this relationship. And there's another thing that I want to show you. Right now here it says like what we have proved is, for any x value which has a modulus less than 1, that means for any x in this interval -1 to +1, we say that this is equal to 1/1 minus 6. This is a very nice result, right? See, if you choose a certain value, let's take -0.5. So this result says that if you consider the series and if you expand the terms, then it will be -0.5 plus -0.5 to the power 2 plus -0.5 to the power 3. Likewise, if you add these terms up, then you will end up with 1 divided by 1 minus -0.5. Okay, so this is kind of a very nice result. Okay, and see, this is also true for x equals 0 case. Can you tell what will happen if you put x equals 0? Now here this series I made a mistake. This series starts at 0, okay, but here I mentioned it as n equals 1, but actually it should start at 0, right? So here you will need an additional term which is -0.5 to the power 0, that is equal to 1. Okay, so what about x equals 0? Right now, if we substitute x equals 0 to the right hand side, then it will be equal to 1/1 minus 0, and that is equal to 1. But if we substitute it to the left hand side, you will get this one, right? This one. So don't we have like now here, if we expand the series, it will looks like this. Okay, so if we have 0 as this basic x variable, why don't we get 0 all, like for all the terms, why don't we get 0? But if we get zeros for all these terms, then this equation will no longer be satisfied, right? Because in the right hand side you have 1, and in the left hand side you have zeros everywhere, right? So where did we do the mistake here? The thing is, now when substituting such a value, it is not a wise idea to substitute directly to the series notation. What you should do is, you should first expand the series and then substitute for x, right? So if you do it in that way, you will not encounter such problems, right? Then what you will be doing is, you are going to substitute x equals 0 for this summation, and here you already have a number 1, and that is not going to change no matter what variable value that you are going to substitute. So the other terms will be 0, and you can nicely see that the equation is satisfied, right? The left hand side will give you 0, and for the right hand side also, when you substitute 0, you will get the same answer. So simply this result is true for any x in between -1 and 1, right? This is the notation for element. So this represents, like, this is the representation for saying x is an element of the set -1 to 1. Okay, so this is very, very important and you must remember this result. Okay, right.